Welcome to the PetroPapers podcast. Say that 10 times fast. This is where you get your dose of oil and gas intellectual stimulation by asking the technical questions. I am Yogeshri Pradhan, and with me here today, I have Mathias Carlsen and Braden Bowie from Whitson and Apache, respectively. Before I take a deep dive in the questions, I want to talk about how the topics of this podcast is covering numerical RTA. And I have the experts in this podcast. Now I'll give an introduction about Mathias and Braden. Mathias is a general manager of Americas and a PE consultant at Whitson. His main idea of work involves reservoir simulation and equation of state fluid characterization. Over the last 3 years, Carlsen has consulted on and supervised a wide range of projects related to PVT and tight unconventionals. Worth mentioning is the basin-wide EOS model developments in the Bakken, Montney, Eagle Ford, Scoop-Stack, and Permian. He's working on gas EOR huff and puff pilots and field-wide implementation pilots in the Eagle Ford, Permian, Bakken, and Montney. He researches and teaches industry courses on advanced PVT and phase behavior, EOS model development, and gas-based EOR. He holds a MSc degree in petroleum engineering from the Norwegian University of Science and Technology and was a Fulbright Scholar at Stanford. Now I'll talk about Braden Bowie. He has a Bachelor's of Engineering at the University of Calgary and worked at Apache Canada in Calgary, then Apache in Houston, so about 10 years. His roles include being the reservoir engineer for the Duvernay development, then RTA and machine learning for the Midland Basin. His current role is the lead reservoir engineer for the Midland Basin, and interests include playing hockey, hiking, and skiing. Welcome to the podcast, you two.
Thank you.
Thanks for having us.
I should have mentioned some of my hobbies. Mention my soccer hobbies there as an introductory note, but
I gotta look well-rounded there, right, Mathias?
yeah, exactly.
I'm sure hockey is very common in Texas, Braden. Well, before I get a deep dive at the questions, I wanted to ask Mathias, what exactly does Whitson do?
Yeah, so Whitson is a software and consultancy company that was originally founded by Curtis Hayes Whitson, thereby the name Whitson, back actually more than 30 years ago. So for those of you who don't know Curtis Hayes Whitson, he wrote the well performance book together with Mike Golan back in the, I think around the 1990s, probably in the late 80s. And he also wrote the SB phase behavior monograph with Michael Brule in 2000. So a lot of people kind of know Curtis as a PVT guru. He's been working a lot in that space, but also been working a lot on that interface between PVT and well performance historically. In general, what we do focus on as a company, especially now recently, has been the Whitson Plus software development, where we, among other things, have implemented this numerical RTA workflow that we'll talk more about today, I guess. So that's where at least a lot of us internally at Whitson are very excited about applying this workflow for field cases in the future.
Awesome. To give our viewers and listeners a background before we talk about the specifics of the paper, I wanted to go through this logically, where Braden, you first published URTEC 2967 last year, and then Curtis, you published ATCE or SPE 205844, both covering numerical RTA in unconventionals. Braden, can you walk me through 2967 pretty briefly?
Sure. So it kind of started with a problem we were having at Apache, where when we were looking at undersaturated oil reservoirs in Midland, the RTA was really engineer dependent. We were getting a lot of different answers. Nothing really seemed to be consistent. So we were trying to make a way that we could do that very consistently, so that we were looking at field to field or trying to do machine learning on it. We had something that was very standardized. And we struggled and banged our heads a little bit. And really, when we started to dig in, kind of some of the assumptions for the classical RTA were being pretty badly violated with the undersaturated oil. So we kind of looked at different ways we could do it, and by using a numerical model to kind of capture the compressibility, the relative perm, and the changes in pressure, we realized we could kind of account for that with a very small kind of unit of symmetry, a single frac, and then try to keep the elements of regular RTA, like the matching that you could match a well in under 10 minutes, so that we could still do it on a couple hundred wells, but really utilize those numerical models where they're strong. So that was kind of the problem where how we got started. And so the workflow ended up using the numerical models in a kind of a very systematic way. And then we were trying to see, did that actually improve the results by getting the engineers to kind of do a blind test? We did seem to improve our consistency for not only the LFP, but the original oil in place. And so that was kind of our checkbox. And then once we had that workflow developed internally, it was really just kind of writing it up into a paper so that we could kind of share it, get feedback, and improve it further.
Awesome. It's really enticing to hear that doing that workflow in less than 10 minutes, and I have over 600 wells to do RTA over. So that's a time saving for sure, and improving in accuracy, which is why I was particularly excited to invite both of you to the podcast, just letting you know. And Mathias, you had an extension of that workflow paper and recently published this at ATCE. So could you walk through 205844, that numerical RTA in tight unconventionals?
Yeah, sure. And also just to provide a little bit of context, I think, Braden, he presented his first paper at URTEC last year, 2020. And I think, at least according to the rumors, he had a little bit of technical issues at the presentation itself. So it's, I don't know, Braden, you have to comment on this, but I don't think the paper off the bat got that much traction just after the conference. But then it took a little bit of time, took around 5 to 6 months until at least I got that paper into my lap. And I read a lot of papers, probably as you'll do as well. But there's seldom that I get super excited about papers, I have to say. So I read it, and the first thing I did was to send it to my boss, Curtis Whitson, and he read it, and he also reads a lot of papers, and he said, "This is the best paper I've probably read in years," and he got very, very excited about it. We saw how we could utilize that workflow very efficiently, also internally for our work, and that was how that started. Probably now 10 months ago, that was the first time I got exposed to the workflow, and really. Through those months, I think the first session I had with Braden was probably either December last year or maybe early January, where we had a few sessions to discuss how we could either improve upon the model, make it more efficient, maybe making certain extensions. And that ATC paper is just summarizing a lot of those, call it findings, and some of those extensions. And that was actually a paper that Braden, myself, and also some other colleagues at Whitson wrote together. And there's, for instance, the low fracture connectivity is one of the things that is brought in as an extension in that paper, one of the key extensions, and that's one example of something that Braden, that was actually Braden's idea, and all the equations related to that came from Braden. And in a nutshell, what that essentially that paper does is to extend the paper that Braden published or presented last year to all fluid systems, so not only black oil, but also making it applicable to low fracture connectivity type of reservoirs. So if you want to have a model that you model with low fracture connectivity, that you can use to workflow in that sense as well. And then it's important to mention that, low fracture connectivity doesn't necessarily mean that you have a fracture with low connectivity, but it just means that you have an additional pressure drop between the reservoir and the well. And so it's just a mathematical or a numerical pressure drop concept, but that's at least how we model it. So that's in a nutshell what that paper is.
Thanks for that clarification. I wanted to follow up with you on that, Mathias, because when you made that extension of Braden's original paper, you also include porosity. So my question for you is, why are you adding porosity or including porosity with that linear flow parameter?
Yeah, so for those of you that read the paper and that have been exposed to the workflow, and also call it conventional or traditional RTA and unconventionals. The two things that we try to quantify is the linear flow parameter, so there's a square of k parameter, and the hydrocarbons in place that we're able to contact. What we do in that paper is that we modify the LFP to also include porosity, and the only reason for that is to make the analysis or the workflow that Braden came up with agnostic to porosity. So to be able to utilize the workflow, you don't even have to know what the porosity is. You say that we want to do this analysis. We want to do it without having any assumptions of porosity. And then after we've done the analysis, then we can talk to our geos, or we can look at sensitivities for porosities after we've done the interpretation of the Bowie diagnostic plot and the workflow itself. So that's the only purpose. And the reason why I like it, I don't know if Braden likes it as much as I do, but the reason why I like it is that it really cleans up and differentiates or decouples the fluid initialization and well perm inputs to the analysis. Then you do the analysis, and then on the back end, you can then deconvolute some of the more geometrical and petrophysical parameters as well. So that's why I like it, and also why we included it in the first place. And maybe Braden can comment on that as well, that I think in the original paper, when you looked at some of these things, the porosity was essentially a input and were kept constant between the different comparison cases at least.
Yeah, no, Matthias, I think it's a good add. I think, as you said, by splitting it where you see kind of fluid properties separate from rock or geometry properties, makes a lot of sense. I know I have to have my LFP tattoo appended to have that porosity in the term. So I'm working on that still.
That's good.
So, thanks for that clarification. I knew that was the first question I asked you, Matthias, whenever I started reading your paper after reading 2967. In the next question I wanted to ask, especially, it's one of those common conundrums of RTA, but with this workflow, I wanted to know, how do you take into account reservoir heterogeneity and stress sensitive properties? And either of you can chime in.
I could take it to start, maybe. I guess when you think about kind of the traditional RTA with square root time, you're making a lot of simplifications for sure there too. So you're saying no flow from beyond fracture tips, it's all linear. So you're starting with kind of a very basic building block, and then you're hoping that your behavior of your real well is close enough that you get information from that. And I think I like that simplicity. And for me, having that numerical RTA, you can kind of design the building block as you see fit. So if you also think it's that simple, you can kind of have that numerical little model with no flow from beyond fracture tips, high fracture conductivity. You can kind of have it as simple as you want. But if you don't think those are good assumptions, there's not a ton you can do on the traditional RTA side. It's hard to adjust the square root time plot for any of those other things. But with the numerical model, like that simple one frac, you can kind of add in any of the complexity you think you are seeing. So if you think you're seeing low fracture conductivity, you can include that for your base model. And then that's kind of your building block as you build up from there. And basically to your question, if you think you're seeing kind of a heterogeneity, you can try to model that in your single fracture model. If you have any, call it geomechanical effects, like you mentioned, stress sensitive, you can incorporate that. So you can really utilize that numerical model to include all the things you think you're seeing. But as long as it's kind of, I would say, simple enough that you can understand how that's building up, or that's a good model that you're going to kind of take to a numerical model, that's where I see the strength. And if you think you can kind of have a big model, say in something like Petrel, then it's never going to replace something like that, but you're kind of trying to simplify it to that basic unit of building block, and that it kind of lets you have the freedom to how you want to design that building block. But that's kind of, I guess, the way I view it, Matthias. I don't know if you guys have used it in a different sense or think about it in a different way.
No, I think that's copy paste on your answer there, Braden. And that's also why. So at Whitson we're organizing this numerical RTA consortium these days with a wide range of companies in North America. And actually, one of the investigation items for further extension of the workflow is these items that you mentioned. where reservoir heterogeneities can be so many different things. One thing it can be is frac heterogeneity, such that you have uneven fracture spacings, something Braden and I have been discussing a lot this week. But it can also be petrophysical layering. It can be also different types of well geometries as well, these EFR models, for instance. And it can also be that you're tapping into different just fluid layers, that you have some gassy layers and some oily layers. So there's a lot of complexities that that goes into that bucket of reservoir heterogeneity, at least in my book. But I think if you start with that building block, however complicated and how much physics you like to include in that building block, and if you have justification for that, then you can use the workflow just in a little bit of a modified way to account for that. That's something that I'm 100% convinced by. The other thing that you mentioned there, Yogashree, that I thought was interesting is, these reservoir heterogeneity and also stress dependent parameters are things that come up very often. How do we account for that? And that's very true. Another thing that comes up a lot is, of course, well interference and parent-child effects. Braden has some good examples from internal use cases of how they can use the workflow to quantify parent-child effects, for instance. We've seen that with many of our clients as well. And I think if you run simulation models where you're just trying to apply this model or this numerical RTA workflow on wells subject to well interference, and you're using that historical data, what you'll end up with is logical outputs. So it is like, even though you have a certain length of the fractures, for instance, what a well that's subject to well interference will output from the workflow is a lower LFP and a lower OIP. So it will still do a very good job, even though there are some of those effects that you're not necessarily accounting for in the building block itself on the get-go.
Awesome. So there's a lot of flexibility that you can do using that numerical RTA workflow in taking into account that heterogeneity and stress sensitive properties. And definitely a problem that is solved from the traditional RTA workflow that I'll admit, because I've struggled with that personally and I get questions about this internally all the time, that how are we taking into account that geology, and how are we taking into account the changes in our permeability over time? That's good.
Just a question on that to maybe Braden, actually, on the same note, on the well interference stuff. Has that been something that's been coming up a lot internally? Because I know how in some of the earlier presentations that you made, Braden, you're kind of doing the numerical RTA analysis on individual wells, and then you're aggregating all of those numbers together, so you get like a pad LFP and a pad OIP, and then you use actually that cumulative or composite number to compare between wells. So I don't know if you could elaborate a little bit on that.
Yeah, for sure. So I mean, as all of you would know, you can drill two wells right next to each other with the same frac and what you think is the same geology, and get different production out of them. So there's always going to be kind of that inherent noise. So we definitely find it handy to kind of add up a lease. So if you have 6 wells on a lease, adding up that total LFP that you generated, adding up the total oil in place that you've contacted, and then comparing that to another lease of, say, wells at a different spacing. And we kind of use it to see, are we efficiently creating LFP? Maybe different frac designs are better at creating LFP than others. And if we're going tighter or looser, are we seeing the in-place volumes correspond to that? If we go too loose, maybe there's volumes that we're leaving behind. Or maybe if we try to cram the wells too close together, we're not actually contacting more volume. When you add up the OIP from all the wells, you're just maybe generating more LFP within that OIP volume. And that's definitely helps us on the economic side of trying to say, how much do we want to stimulate? Are we okay with leaving a little bit behind, or do we need to contact it all? And trying to kind of balance that on a lease scale rather than just a well scale.
Awesome. Well, I wanted to pivot to your paper, Braden. I guess the catalyst that started it all when it came to numerical RTA. Your workflow really changes the perspective in linear flow parameter, because I've seen it as a static value when doing the traditional RTA analysis. However, you introduce the instantaneous linear flow parameter, and whenever we see a bend, for instance, in that instantaneous linear flow parameter, there is a transition from linear flow to boundary dominated flow. And then your workflow also mentions about picking the representative linear flow parameter out of that instantaneous linear flow parameter over time. Could you give some guidance as far as how do we figure out that representative linear flow parameter? And Mathias, feel free to chime in on this one as well.
Sure, yeah, no, good question. So since we're running a numerical model at the exact drawdown of the real well, you have an oil rate and a gas rate and a water rate for every kind of day. So what that allows you to do is compare the actual well's production for oil, gas, and water, but we'll start with oil, comparing that oil rate to the model. And by looking at it as a ratio, that's kind of like a productivity index, which LFP really is a productivity index too. So that's where it's kind of, yeah, not a traditional way to view it, but it's almost looking at how does the productivity look day to day? Is it flat, or are you seeing trends over time? So when we kind of talk about that representative LFP, it's looking at the period we think is infinite acting. So there may be some noise, but where does that LFP appear to be stable, and what value does it appear to be stable around? We also think that it's really helpful to look at the GOR when that's happening, because as the well drops below bubble point, the GOR is going to go up in any case, but it should be tied to the flowing pressure and not kind of continually ramping if you're in infinite acting flow. So you can use the GOR to see, okay, I think I'm still in infinite acting flow. What does that LFP look like as maybe an average in that range? And then we also use cum oil. So between the three of them, you should be able to kind of find an LFP that's a good average in that infinite acting flow. And then that kind of makes the baseline for, then as you start to look at boundary dominated flows, it's deviation off of that straight line or that value of LFP.
Got it.
Very good. And I'll just, you know, the way I kind of think about it a little bit, because I see a lot of the companies that we talked to about this methodology. And also I had kind of the same question, actually, when I read the paper the first time, that this is like a different way of thinking, at least for me, or it was a new kind of concept. But when you do traditional RTA with a square root of time plot, where you're trying to find a slope on that square root of time plot, you could, in theory, with all the noise there, almost from the origin to one of these points, get a new slope every single day, almost, because of the noise that you have there. But what you're actually doing in practice is to find with one representative LFP, as long as that is a straight line on that square root of time plot. And it's a little bit of the same thing that we do here, where you can in that infinite acting period view all the small differences day to day as noise, and then you're trying to pick kind of an average between them. But once that deviation below the straight line happens, that can be the same as when you see the deviation from the straight line on the square root of time plot as well. So there's some similarities there, I think, where probably the new part is this daily LFP concept.
Right. I think that's going to be very interesting for our listeners and for our viewers as well. Just that new perspective on linear flow parameters, the instantaneous nature of it too. Now I'm going to pivot to you, Mathias.
Okay.
In the SPE paper that you presented at ATCE, you mention in the workflow, or there's a field example in the paper where there's low fracture conductivity. And in Braden's workflow, he talks about running a model with high fracture conductivity or infinite acting model. So I was just curious to know that in reference to that field example, why did you continue to run a numerical model with that low fracture conductivity?
Yep, so that's a great question. So the most important thing to emphasize is that every time we run this workflow, the default is to run it with a finite or an infinite connectivity fracture. So what Braden originally proposed. In some basins, however, especially we do a lot of work up in Scoop Stack. There they add something to their completion practices that make some of the wells produce this kind of gummy bear stuff at surface, which at least it looks like if you just look at traditional square root of time plots and also the GOR profiles, it can be some evidence that there a low fracture connectivity here would be required to get good history matches or good analysis from the numerical RTA workflow itself. So that's the justification of why we wanted to include it in the first place. But I think in January or February, I talked to Braden about that, because we had some companies where that definitely had to include this for almost every single well in this region, whether that's being geology or completions or something else. It really doesn't matter. It was required to have some kind of additional pressure drop between the reservoir and the fracture, which is all FCD or a low FCD really is. And through that discussion, Braden has actually done some thought process and some work on that. So he sent over some derivations, and that's included in the ATC 2021 paper, and is also what we've included in the workflow now. So if you see some evidence of that, you can also include it. So there's nothing else than that. And for that field example, it was almost arbitrary that that's a field example that has or requires that low fracture conductivity assumption. So yeah, that's a short story. Maybe Braden also can shed some light on that derivation that you did, or that conversion that was required to be added to the workflow for low FCD to work.
Yeah, so basically, as you said, Mathias, I agree. It's kind of neat that you can add the low fracture conductivity if you're seeing that, and then that's just part of the building block you're looking at different wells for. But yeah, I won't get too much into this kind of, but we were looking at essentially the same problem for one of our fields, and we noticed that depending on kind of how you have fracture conductivity versus the reservoir permeability and some of those, to kind of make that a standardized property or unique, we needed to make some adjustments, but I think it works well with the workflow. And then, yeah, depending on what you view your reservoir permeability as, then it applies that fracture conductivity that still matches. So when you get into a numerical model, you don't have to play with it. That fracture conductivity should give you a good match in that numerical space as well.
Now, thanks for that clarification as well. It was something that really, I wouldn't say confused, but I would say it was a different part of the workflow that there was a difference from what I've seen in the original workflow versus what was presented in this paper. So I really appreciate that clarification and just really the flexibility, what we can do with the workflow. And I know you touched upon this, Mathias, in like a few questions ago, and Braden, feel free to jump in on this. I know I've exhausted you guys with a bunch of questions. So, and it's probably just the beginning too, but I wanted to ask, what are some of the new applications of this workflow compared to what we haven't seen in the past? I mean, it's pretty self-explanatory from the workflow itself, but what are some applications that you guys can talk about that we really haven't seen in the past, especially with RTA, where we haven't had much advancements in RTA over the past 10 years?
Yeah, I'll share my opinion on that first, and then Braden can close it all out, I think. But in short, what is really unique with the workflow is that it unites numerical reservoir simulation to RTA. That hasn't been done before in such a seamless manner. What that solves technically is an elegant way to deal with everything that's complicated with RTA, which is the combination of superposition and multi-phase flow effects. And then the beauty of that is that Braden and I and everybody else that are just humans and not computers, we don't have to do all the complex math. We're essentially delegating all the complex math to a computer. So we're leveraging that, and the numerical simulator are doing all the heavy lifting for us. And we can focus on the interpretation part, which is picking linear flow parameters and OIPs, or drained hydrocarbons. So in my opinion, that's the three kind of main things that makes it beautiful. The other thing, probably the last thing, is that since it's so systematic, you save so tremendous amount of time. And I know that for sure, because I can just, historically, 5-6 years ago, we could run these models as consultancy projects. We could have 2-3 months of consultancy projects to history match maybe 12 wells like this. Now, I can guarantee you that I can do it in less than 4 hours with every single nuts and bolts that you have there, from the PVT to the bottom of pressure calculations and everything with sensitivities and whatnot. And that efficiency gain is at least amazing when you're doing this day to day, and it's also been cool to see in practice the last year. So those are the few things that I would say is tremendously new.
I'm glad to hear that, Matthias. It's awesome to see that leverage of being able to do it that much faster and still get a good result. So I guess one of the things I kind of view as a future where I think it could go, but we haven't got there yet. But I know in the past for either numerical models or RTA, it was we look at this well alone, we match this well, and then we kind of pick up shop and we go to the next well. Some of the properties like rel perm or PVT should be very similar or the same if it's, call it the same formation in the same field. But it definitely is you look at it on a well by well level, and then you just hope to maybe have standard properties across a field. But now that we've got it into some of the softwares like Whitson, I think we're in a place where we could potentially run RTA on a field of wells. So you could have 50 wells and call it the Wolfcamp B in a certain area of the Midland Basin. And instead of history matching one well at a time, you could be history matching all 50 at once. So trying to see, okay, if we tweak the rel perms for all of the wells at once, does that get a better match for oil and GOR, given those drawdowns of all 50 wells? So I think there's a way where we could move beyond just looking at it well by well and be matching kind of the best properties for a field as a whole. And maybe they wouldn't be the best properties for each well, but by being able to generalize it like that, especially on the upstream side, okay, what's your next pad going to look like? What's your next lease going to have the properties for? I think that'll be a really key piece that could lead to a lot of insights. That's what I'm excited about taking it to anyways. So.
In your paper, you do talk about those relative differences between wells on a pad. So that I can definitely relate to that. It is a system at the end of the day.
Just to add one last comment there from Braden's comment that I thought was very good is that at least historically, in my experience at least, maybe Braden can chip in there as well, is there's kind of two different narratives that are sold to you in the oil and gas domain. It's either to create one or two of these super complex models that maybe has all the wells in a pad, all the geomechanics, all the petrophysical properties, trying to model everything from injection to production. And at least my experience when either working with that kind of models internally in our shop or externally as a third party, either auditor or providing PVT expertise or whatnot, is that it tends to be an extremely non-unique exercise. And it's also not a very scalable exercise. And it's also very hard to QC it fast because there's so many assumptions going into it. Imagine having a different transmissibility multiplier on every single fracture. It's super difficult to use for value adding internally, I would say. And then the other narrative, which is a little bit more along the way that Braden has talked about now, would be to do simpler type of models, but extremely technically rigorous. But they're fast enough so you can actually do it on every single well across a plane, hundreds of wells. And that's also the beauty of moving a lot of these things on the cloud, that you can essentially parallelize a lot of these activities. So even though you do 50 wells, like Braden say, or 100 wells or 500 wells, you're actually able to run them in a systematic fashion. So that's super exciting, and definitely where I see the future of that workflow, and probably just even just regular RTA in general as well, like picking LFPs or slopes on the square root of time plot one by one is also a tedious exercise. So you should be able to do some of even that stuff on a automated or a multi-well basis, in my opinion.
I am very excited about that when you mentioned the automated process, because I have gone through 600 wells one by one, and it's fun.
That's one way to put it.
That's one way to put it.
Yeah, that's for sure.
Yeah. Well, that's a wrap with our inaugural PetroPapers podcast episode. I want to thank Mathias and Braden one more time for letting me pick their brain on what exactly they wrote these past couple of years. And I wanted to touch upon something that Mathias talked about before. There is a numerical RTA joint interest project that Whitson is a part of, or that Whitson is hosting. So if there are any companies out there that are interested, feel free to check them out. I mean, I'm going to say that because I think they're this is a workflow that really does excite me, and I think that's going to make a big difference in how people perceive RTA for sure. So thank you so much, both of you, and yeah,
Thank you for having us.
of course. All right, viewers and listeners, feel free to let me know what you think of this inaugural podcast. And once again, I'm Yogeshri Pradhan, and I'm signing off.